Hello, this is Mark Burrows. I'm a project manager with the International Joint Commission's regional office in Windsor, Ontario. The IJC is a partner with Sea Grant and the Great Lakes Commission on this webinar series. Welcome to the third webinar of the 2019 webinar series hosted by Great Lakes Sea Grant Crude Oil Transport Network. Our previous two webinars with Guy Meadows and Stephen Keck are available on the website with captioning. The Crude Oil Transport webinar series is meant to provide the latest research and resources to stakeholders in the region to inform decision-making around this complicated and complex issue. Anyone with a vested interest in how crude oil and associated products move throughout the region will find the content informative. It's my pleasure to introduce Mr. Bill Hazel. Bill is the Vice President of Marine Services for Marine Pollution Control, a full-service environmental organization founded by Dave Usher in Detroit in 1967. In his 28 years of service to MPC, Bill has responded to numerous oil and hazardous materials spill events in the U.S. and overseas. He has also participated in research and development programs for oil spill technologies and tactics involving heavy oils and oil spills in ice conditions. Bill is here today to tell us about oil spill response capability for heavy oil products. And with that, thank you so much, Bill, for helping us today, and please take it away.
Thank you very much, Mark. And I'd like to begin by thanking the Michigan Sea Grant Program for having me here today in their lovely offices in downtown Ann Arbor, and for carrying forth the mission of these seminars as they do. To give a little perspective about how I'm going to approach this presentation today, I just want to tell you a little bit about myself. I'm not a scientist. I'm an oil spill response professional, and I've been doing it for 28 years now. And the experiences that I'm going to present here today come from the perspective of field operations. Now, I will be touching on the science because we use that to some extent in order to guide our actions in the field. But really what I'm going to talk about here today is about the tactics and techniques that are applied and the capabilities that are available here in the Great Lakes from the oil spill response community. I'd like to start with this slide here and just to present the idea that this is the first concept that we sort of look at when there is an oil spill and we start addressing it, that it's not simply the slick that is distributing across the water surface, but there are also other actions that are taking place, including evaporation. Part of the oil will evaporate during this process. Some will dissolve into the water column, and some will actually sink and be deposited on the bottom. And all of these actions, these physical properties of oil must be considered when we are selecting tactics and techniques to respond. Looking at that from the perspective of heavy oil, we'll look at all of those concepts as we move through here. So these three principal concepts also apply to how we address assigning tactics and techniques to an oil spill response. The three important concepts are the viscosity of the oil, which refers to its resistance to flow. Its volatility refers to how quickly the oil will evaporate in the air, and its toxicity refers to how toxic or poisonous the oil is to either people or other organisms. Volatility is something I'd like to highlight generally from the responder's perspective, because this is an interface that involves the health and safety of the personnel that will be responding to the spill. So a more volatile oil has to be treated in a specific way relative to protecting the responders during the response operations. And hopefully as I get through this, I'll start to kind of draw out more clearly how viscosity and volatility is addressed in that process. So oils are generally classed for this purpose as in 5 groups. And what you're seeing now is the first 3 groups, which include group 1, non-persistent light oils, and these include like gasoline and certain condensates, up to group 2, which will include diesel, number 2 fuel oil, and light crude oils, and up to group 3, where medium oils are considered. So these include most crude oils and what's called intermediate fuel oil, number 180. And I think you can see from these slides, and I know they're a little busy, but you can see that what's happening as we move up the scale here, oils are becoming thicker, they're becoming more, possibly less volatile, but they're also becoming of a heavier viscosity and probably a longer sense of persistence to their presence in the environment as well. So these are the 2 groups that really are classified as heavy oils. And we're referring to the heavier crude oils, number 6 fuel oils, and bunker Cs. As you'll see, in these cases, little or no evaporation or dissolution of the oil is likely to take place. Heavy contamination of the intertidal areas is likely. And this implies severe impacts to the waterfowl and fur-bearing mammals. Long-term contaminations of sediments are possible. It will weather very slowly, and shoreline difficulty cleanup will be difficult. And then we move into the group 5 oils. And these oils are specifically classified in that their specific gravities are greater than that of the water into which they may be spilled, which means that they will sink. So most of us are familiar with the idea that oil spills are floating components, but they're not always. And so this presentation will be addressing that. And another important classification in that regard generally is the idea of an oil being persistent or non-persistent. And this is amongst the group of 5 different oil categories. Group 1 oils are not a persistent oil. Their evaporation quantities and qualities are such that the majority of a spill will evaporate with no actions taken at all. This implies an acute toxicity to the environment, but not a persistent problem. Whereas the oils that we're concerned about, most specifically group 4 and group 5, these are persistent oils. These are oils that are going to stay in the environment for a very long period of time. Not a lot will evaporate and not a lot will dissolve. As you can imagine from a response perspective, you're looking at a longer duration of an operation and a longer slog and a harder workload. So to summarize what I just covered there relative to some of the classifications of how we look at heavy oils and what that means, for groups 4 and 5, the viscosities are likely to be very high, particularly after weathering and the release of the light ends, and when temperatures at the spill site are low. In terms of volatility, the heavy oils will tend to be less volatile than oils in groups 1 through 3, with a very important distinction, and that is that certain grades of crude oil are mixtures that may include highly volatile light ends mixed with the heavier components. And this is what I was trying to imply when I said that this volatility issue is very important to the response, to the responders who have to address the spills. And then in terms of toxicity, these heavier oils will have a lower acute toxicity than the first 3 groups, with the important distinction of those high volatile fractions. And then persistence, heavy oils should be considered as persistent oils. And so as we go through the presentation, we'll come back around that word of persistence and what it means to responders. So I'm going to cover, for heavy oil spills, the response methods that are generally associated with responding to them. And these will include containment and mechanical recovery on water, mechanical and manual recovery of oil on shores, in situ burning, and non-floating oil response techniques. What I will not be covering relative to the Great Lakes environment is the issue of dispersants. And dispersants are surfactant chemicals that are applied to oil spills and which allow them or force them or cause them to break up into smaller molecules that then are hopefully distributed through the water column. This type of approach will not, in my opinion, ever be seen in the Great Lakes. They are not approved for the Great Lakes due to the shallowness of the water bodies, the fact that the Great Lakes provide fresh water, potable water for communities, and so on and so forth. So they will not be applicable. It is not something that I consider is relevant to the topic for Great Lakes heavy oil spill response. In order to give those who may be participating who are not really familiar with oil spill response generally, I'm going to start with this concept of containment booming. So basically, a containment boom is a barrier that is placed across the water body that is designed to hold in a surface oil spill and direct it to a position where the oil can be mechanically recovered. In this case, the slide we're looking at, there's a skimmer positioned there from a shoreside recovery perspective. And in that pocket is where gathered or accumulated oil will be recovered by a mechanical device. And in this animation, we're seeing that mechanical recovery device, how it works. Basically, there's a weir presented there, and the oil, which is on the surface in this particular case, pours over the edges of the weir and then is delivered through a hose mechanism to some form of temporary storage device. So that's kind of oil spill response, mechanical recovery, and containment 101 for those who are participating who may not be familiar with those techniques. Now, to break that down a little bit further, there are typically two types of mechanical recovery devices that are employed for oil spill response. This first one is a weir skimmer device, and as you can see, the idea is that the oil will pour into a weir right at the oil-water interface at the surface of the water, and that it will be pumped by that orange pump mechanism there to this temporary storage device. And the alternative to that is an adhesive type of an oil skimmer. And in this case, what we're looking at is we're looking at a drum skimmer. And that round drum that is positioned within that collected oil pool will slowly rotate. And as it rotates, the oil will adhere to the surface of the drum because the drum is oleophilic. It likes oil, it loves oil. And then it is scraped off into a hopper basin, and that hopper basin then has a pump or a vacuum device, and it's recovering that oil as well. So these are both typical oil spill mechanical recovery devices that are used in the field, and they can be adaptable for heavy oil applications. That's a heavy oil you're looking at right now, some type of oil that was involved in a steel making process. And the other thing I really like about this slide, and I've always liked about this slide, is it shows that laminar flow by that swirling pattern, which is as that drum is just simply spinning, there's no other energy force other than that current and the laminar holding together of that oil on that surface that's drawing it into the skimmer and delivering it to the storage device for recovery. So the issue of viscosity when we're talking about heavy oils is a critical component of what we want to talk about here. This particular quote from Tim Wadsworth presents the idea that viscosity will have a considerable effect on the efficiency of virtually any kind of recovery devices. And oils with high pour points or high viscosities, like heavy crudes and fuel oils, they don't flow easily. And if the ambient temperature is below the pour point, the oil will effectively behave almost as a solid and hence will be difficult to recover. And he's drawing this experience from the Exxon Valdez, where many of these techniques were attempted, and as the oil became weathered and became heavier and heavier, the skimmers and the pumps and the transfer equipment all became harder and harder to work with, and hence the efficiency of the operation was diminished. Here's a slide that presents the principle of friction loss. And what that's really talking about is that thicker, heavier materials will be harder to pump through hoses and pipes than thinner devices. Imagine it, I thought about it last night, imagine it, the difference between drinking a glass of lemonade versus drinking a strawberry milkshake. So you know that you have to apply more force as the liquid that you're trying to transfer becomes thicker. Now in this slide, if we kind of draw from the y-axis, which is from the x-axis, which is the horizontal axis, if we're trying to pump at 200 gallons a minute, the bottom curved line is indicating pressure loss or resistance to flow versus of a thinner material than the upper line, and the difference is quite considerable with a thicker material. That more resistance is there, and therefore more energy is required in order to make everything move through the equipment. So this slide represents two types of pumps, which are critical to maintaining the flow of all this. One being an axial flow pump on the left, and the screw positive displacement pump on the right. And their discharge pressures are reflected as as 115 psi for the axial flow pump versus the 150 psi for the positive displacement pump. So if you have a thicker material, if you're dealing with a heavy oil, you want to select the types of pumps that have the higher pressure ratings in order to ensure that we can keep the material flowing into the tanks and storage devices and being recovered from the field and passing towards its eventual home, which will be a temporary disposal site. Now, those principles of placing high pressure pumps and pumps that can handle these thicker oils in an early sense was presented as an important aspect of developing skimmer systems, which were used or can be used in heavy oil situations. So these particular pictures are from a company called Lamor that is out of Northern Europe. They're presented to me, they're a partner of mine in dealing with heavy oil response technologies. And what they've done is they've taken one of those positive displacement type pumps and they work it into their oil spill skimmer units. So I have a video here that presents what they are able to do. And I think it's very interesting for folks to see the thickness of oil that can be overcome with this technology. So what we're looking at right now are discs that are flowing through oil spills in Arctic environments and very, very heavy oil spills. And then they are being transferred into bins, scraped off of the brushes that are collecting the oil. And from there, they will then be transferred through pumps and piping systems. And I think you can see that this is a very, very, very thick oil that they are dealing with here. Not sure exactly what it is, probably a bitumen type product, but you can see what can be achieved by integrating those technologies together, the high pressure pumps and the skimmer devices that can handle the heavy oil. So I'll just let this play out a little bit more to just show you the types and thicknesses of oil that can be overcome in that regard. Now, those technologies are very refined and they're very unique. And I just wanted to let folks know that, that these technologies have been deployed within the Great Lakes. In this particular case, U.S. Coast Guard Research and Development field demonstration in the Straits of Mackinac 2012, that is one of those skimmers mounted on a vessel that is positioned generally in Escanaba, Michigan. And so this demonstration was to reflect that those technologies were applicable to our Straits of Mackinac area, to our Michigan environment. They were deployed in the middle of winter. It was a particularly bad winter. There was 18-inch block ice out there, and we were able to mount the equipment on the vessel of opportunity, take it out there, and use it in that environment. I also would like to point out that subsequent to that, some of this technology has been acquired and is positioned in the Great Lakes. In this particular case, this unit is owned and it is positioned in northern Michigan by Enbridge Corporation. So they have invested in this technology. They have invested in training folks in this technology. This is my company participating with them in Sheboygan, Michigan, to deploy that technology. So 2 of those skimmers, those heavy oil skimmers, ice-capable skimmers, are deployed up there. But I also don't want to give you the impression that those are the only heavy oil skimmers that are in place in the Great Lakes. There are many of these types of skimmers and many responders who have this capacity. In this particular case, this is a stock photograph from Lemoore demonstrating that one of their mid-sized skimmers is capable of handling these heavy oils. And here, this is my company's deployment of some of our heavy oil capable skimming systems. I would say of the skimming equipment that I own in-house, approximately 30 to 40% of it is currently heavy oil capable. The rest of it can be used in heavy oil with adaptations, but some of it is specifically designed. And I think that's the case with other OSROs in the area as well. So I want to reflect, because the topic of the presentation is heavy oil spill response capability, that it exists. And not just the knowledge of it and the research and development of it, but it's here. And trained and qualified people know how to integrate those systems together to address the issue. So what it all comes down to from that perspective, relative to mechanical recovery, I have put together this for us. So we have a water body and we have an oil spill on top of the water body, and then we're going to select an oil skimmer. And if this is a heavy oil, then we're going to select a heavy oil skimmer. That skimmer will deliver product to some form of portable storage tank. And in this case, it's a tank in and of itself. Now that tank, which is now accumulating this heavy oil, which needs to be moved, it's going to have a specialized pump apparatus that's applied to it in order to deliver that material to over-the-road tank trucks or other transport devices, with the goal and the objective of getting that oil back to a reclaim or disposal facility. So throughput efficiency is the name of the game. And understanding the throughput efficiency of heavy oil as being more difficult than a lighter oil, just relative to its viscosity and its handling requirements, is something that is built into what I'm talking about here today, but also our approach to heavy oil response generally. And as we go through the presentation, hopefully we'll give a better idea of all of the aspects and facets of what's happening in the Great Lakes between the OSROs and the oil transporters and the regulatory people. But I would like to highlight that this concept, that as the oil becomes thicker and these transfer methods all become harder and everything starts to get more and more difficult, you can imagine that in addition to just technology, manpower has to go up. So if a skimmer only has 1/2 of the efficiency in a heavier oil that it would have for a lighter oil, then you need 2 skimmers or 3 skimmers. And if you need 2 or 3 skimmers, you need crews to support them. So as this oil becomes heavier, then the workload becomes greater. It seems apparent, but I want to break down the idea here of how we think, how oil spill responders think about the problem. So just briefly mentioning that, we've talked so far about recovery of oil on water bodies and how it's accomplished. obviously the entire thing also translates to shorelines. So here's an oil spill. I believe this is the Prestige spill in France. When heavy oil is deposited on a beach, it's persistent. It's not going to evaporate. It's not going to go away. And methods for its recovery must be devised. In this case here's a slide from 1989. This is an Exxon Valdez slide. So this is an Alaskan shoreline, and this is a shoreline washing operation of washing a relatively heavy oil. I do not know if the Exxon Valdez crude fell into group 3 or 4, but it's a heavy oil for our purposes of discussion here. And this is the kind of operation that can be anticipated with a heavy, persistent oil. Here's another picture. Again, I think this is from the Prestige spill. And this reflects a methodology that was employed in order to recover this heavy oil from this rocky shoreline. They determined at this point that this would be the best way for folks to be recovering this. And I'm going to reflect on that in the next couple of slides about why a methodology like this, a manual methodology, might be preferable to another methodology such as this. This is a mechanical recovery of an oil deposit on a beach. And this particular picture comes to us from 2010, from probably the coast of Louisiana, maybe Alabama. But this is from the Deepwater Horizon spill. So these mechanical methodologies may be applicable to cleaning up a shoreline as opposed to those lighter footprint, no pun intended, technologies where manual recovery is taking place. And here's another picture of the Deepwater Horizon spill and a beach recovery operation. And as you can see, in order to mediate that heavy oil from the beach, a considerable mechanical presence was required on the beach. And as you may imagine, a considerable mechanical presence on a beach will have some form of derogatory effect on the beach itself as well. There will be a give and take between the idea of how to recover the oil and not doing too much damage to the beach by driving too much heavy equipment across it. And that entire concept is captured by oil spill responders and by the community that addresses these by what is called Net Environmental Benefit Analysis, or NEBA. And what NEBA is a structured approach used by my community and stakeholders during oil spill preparedness planning and response to compare the environmental benefits of a potential response tool and then develop a response strategy that will reduce the impact of an oil spill on the environment. So there are the 4 stages that are identified here, are to compile and evaluate the data to identify the exposure scenario, and then you identify potential response options, and you can then understand the potential impacts from the scenario. Then you will predict the outcomes from the given scenario to determine which techniques are effective and feasible. You're going to balance some trade-offs by weighing the ecological benefits and the drawbacks resulting from each feasible response option that you have. And I want to call out that word feasible, okay? Because this is not a smorgasbord of availability of the entire spectrum of response tactics are available all the time under all conditions. When you say feasible, you have to weigh in with the OSROs, with the response community to say, what can we do? What do we have here? And what is, no, it's 85 hours away from us right now, but this is here now. So feasible is a very important word in that particular concept. So the bottom line is that a bunch of people will get together and talk about what is at risk, what can be done, and what can be brought to the table, and what's the best choice to do it. And NEBA gives us the tool and the discipline to do that. So We start NEBA by looking at the environmental considerations. What is going to be affected by the spill? We have a tool in the Great Lakes. It's produced by the National Oceanic and Atmospheric Administration called IRMA. It was developed out of the Deepwater Horizon incident, but it has since been exported to various regions in the country. This particular slide shows us some of the environmental sensitivities that are near Frankfort, Michigan, and Betsy Lake. So those colored areas are identifying the types of shoreline and the protections rating of those particular areas. And you can see red is a high protection. It's a very sensitive environment, whereas blue has none. That particular logic is something that's built into their system. And then the green, which is a low impact shoreline. So we start there by looking at what's going to be impacted, and then we start using some of these tools to say to ourselves, what would be the best selection? First of all, we have to select what can we bring here. So this particular table, and I would like to apologize for the quality of the graphic and to encourage you to email me later on if you want the source document. This is looking at a series of different recovery techniques. And if you notice at the top, it says, what is their relative impact in the absence of oil? So basically what this table is saying is it's saying that you choose this selection and you look at these criteria, and that technique, even if there isn't any oil, will have this impact on the area, on that particular site. So we look at these things in the absence of oil. We say, what will the technology, what will response technique actually do in terms of damaging the environment? And that starts, all of NEBA starts from the concept of take no action. And this slide kind of implies that. Now, this next slide is interesting in that it's saying, what are these techniques? What is their capability versus what are their operational limitations? So it goes back to examining what the feasibility of a technology will be. And so what I'd like to highlight here is that if we look at the top one, open water skimming, okay, and then we look at the other criteria that's being applied to it, and it's very hard for the reader here probably to view this, but I'm going to tell you what it says is debris or broken ice. And basically what they're saying is that if you want to do open water skimming in debris and broken ice conditions, that there will be high amounts of operational limitations to mechanical recovery. So this is what we're talking about there. That orange object being deployed from that crane, that's the vessel U.S. Coast Guard cutter Hollyhock, and that's the Mackinac Bridge in the background there. This is part of that demonstration in 2012. That skimmer is going to be deployed into that broken ice patch there with the thought that it would be used for a recovery operation. However, we'd like to present to folks that during an ice condition, an oil spill in an ice condition, the ice will prevent the oil from getting to the skimmer. In this particular case, the skimmer is positioned in some simulated oil. This was some peat zorb and some oranges there. But once that skimmer has completed recovering or separating the oil out of that recovery pocket, all the ice all around it is going to hold oil from getting to the skimmer and prevent recovery operations. So in this case, in the NEBA benefit here, this skimmer, this technology, this tactic might be ruled out to some extent because it's not going to be very effective. In other words, the ice is going to prevent that technique from working. So that leads us to what would work. And so the concept is, the idea is that one of the techniques that is used to recover oil is this idea of in situ burning, which is basically setting the oil on fire in order to allow it to be, it will be delivered into the environment, it will be dispersed through the atmosphere, be removed from the waterway. So it is a technique that in certain conditions, and applying this NEBA concept, it is one of the only tactics or techniques that may be useful to reduce the amount of oil that is in the environment. So what I'm calling out here is that it says in ice-covered water or in a marsh, in situ burning could be the only spill response method that is available. So it is one of the tactics that has been considered for oil spill removal in ice in the Great Lakes. Now, the general principles of in situ burning include that all oils can be burned, but group 1 oils are much too volatile to safely use in situ burning tactics. Heavy oils may have lower burn efficiencies, but they can still be burned. Slicks have to be at least 2 millimeters thick to allow for burning. Windows of opportunity are short for applying this tactic, maybe less than 72 hours, although in Arctic conditions, those windows of opportunity may be extended. And then the bottom sentence here, the bottom point here is that in situ burning definitely requires stakeholder consensus. So all members of the incident command for the spill must present their cases pro and con, and the agreement to be able to use this technique, applying the net environmental benefit analysis principle to it. That is something that will need to be obtained. And I will point out that in the Northern Michigan region, that this dialogue and this discussion is definitely being had by that area committee. I don't know if Steve mentioned it, but it is definitely something that is being considered for the region. Now, when this occurs, when this is considered, special considerations must be given to allow for it to happen. Basically, this is administered through the SMART protocol, special monitoring of applied response technologies. And generally what we're looking at here is that the smoke plume and any burn residue must be monitored in order to ensure that the safety of local populations, and that what we want to do here is reduce ecological damage, that is being achieved by what is being carried out. Now, in the demonstration that took place in 2012, this technique of in situ burning was tested. And by that, I mean that the equipment was tested. Nothing was burned. No oil was present. This was an oil-free demonstration. So that is a in situ burn oil boom. And that boom there is capable of withstanding the high temperatures that would occur when an in situ burn is going to take place on a water body. It's a Kevlar fabric. Those are stainless steel floats, and it is deployed in this manner. It's being deployed off of 2 local Escanaba-based tugs, both of which are ice-classed in the Straits of Mackinac area. We're pulling the boom out with the one tugboat, deploying it from the stern of the second tugboat. And here we are. Here's an aerial view of us cutting a small portion of the ice out of the ice flows. What we're going for there is that would be an area of ice that has oil within it. So here is a video of taking that ice from that ice body and towing it out into the straits. The weather was significant on that particular day, probably 3-foot swells. And as you can see, the boom is able to hold that material in there to facilitate the burn. So here's a test in the Straits of Mackinac of that technology. And there we have an example of an actual burn. This is in Europe. put out by an organization called SINTEF. So they are using that in situ burn boom, and there is oil in that particular area, in that ice flow, and they are burning it. And as I said, in those kinds of conditions where mechanical recovery may not be useful, then these types of ideas and these types of response techniques are applicable to the subject. And just this slide here shows that it's not necessarily only applicable to open water recovery operations. This was what we call a thermal recovery operation of a crude oil spill on a small creek in Ohio. So in this particular case, it was determined that the best way environmentally to deal with that oil was to burn it off of those shorelines. So it has been applied in the Great Lakes in open water conditions, I think in the 70s. I don't have any provenance on that, but this particular case was probably around 2006. So that brings us to the final response consideration that I wanted to address today, which was the particularly heavy oils, the group 5 oils, and other oils as well in the groups of group 4 and possibly into group 3, is non-floating oil, oil which sinks, which may seem counterintuitive to many people that oil floats. Well, it doesn't always. There are reasons why oil may sink. The first one is clearly that its specific gravity is greater than the specific gravity of the water into which it has been placed. And the second is that an oil that may have a specific gravity that would generally allow it to float may interact with sediments present in the water and agitation. And as that sediment picks up into the oil load, that may cause the oil to sink as well. So this table from the National Academy Press shows the relationship between the density of oil and the salinity of water. And then I've positioned some API numbers on the right. The lower the API number, the heavier you can anticipate the oil. So if you look at the two green lines that I just introduced into this, our Great Lakes do not have a high salinity, which makes them more prone to a sinking oil as opposed to seawater. So anything on the vertical line, the crooked density versus salinity line, above the red line, it will not float. Below the red line, it will float. So you can see that in the Great Lakes, we have a greater propensity for density or for oil in fresh water, that it could have sink rather than in seawater, which is a denser form of water. And then this table here brings up the idea of oil to water density is fairly clear. I mean, if it's less than 1, the majority of the oil will float. That's on the left-hand side of the table. If it's greater than 1, then the majority of the oil will not float. However, as currents are applied and oil is suspended in the water column, the oil may sink to the bottom. And then if sediment interaction occurs, then even with the oils with a specific gravity of less than 1, if that interaction is high, the oil will sink. If it's low, it might form tar balls, and that carries through. The idea is that there are several reasons why oil may sink, and so looking at all of this and understanding that these conditions could occur, United States Coast Guard, who classifies OSROs, actually in 2016 made a special classification for OSROs, or oil spill removal organizations, company like mine, which are response organizations, that they be classified with capacities to deal with these sinking oils. And there are numerous oil spill response organizations that do this, and by numerous, I mean there's probably 10 or 15, but they do have presence here in the Great Lakes. There is that capacity. So in terms of the problem that's being presented here, On the left, we see a floating oil, and the oil is visible, and the currents and winds will drive its direction. Therefore, we know where it is traveling. We know where to send response equipment. We know how to address that oil mechanically from the containment perspective. But on the right-hand side, we have this condition where oil is no longer visible to us. And so therefore, the detection and the forecasting of where oil will be and how to react to it becomes exponentially more difficult. This is a slide from Puerto Rico of a heavy fuel oil spill in those dark ridges there. That is submerged oil that is contained within the surf zone. And these are some photographs of that oil. This photograph is of that oil in that surf zone. Now, what was particularly interesting about this is that at night the oil would sink, but during the day, as the sun heated the oil, then its viscosity would lower and then it would float. So it was a sinking and floating oil that was being affected by temperature. And the other thing that's important about this is, so the fundamental difficulties that I'm trying to imply here are that in terms of detection, trajectory, forecasting, and tracking of a heavy oil spill that is sunk, there is no single reliable method for all situations, and locating and tracking is critical to guiding tactical response efforts. Containment is a specific complication in the method, in this strategy. Oil on the bottom, it hopefully will deposit in areas where current slows down, and there will be deposition areas. But in order to create those containment devices, whereas an oil spill an oil boom on the surface is fairly straightforward situation, on the bottom it gets a little bit more difficult. Recovery, the techniques are complex, they are expensive, and they require robust logistics. I'll get to that with some photographs here. And then waste management techniques. These types of operations from the bottom of water bodies are going to result in the gathering of large amounts of water and particularly of sediment. And that all has to be factored into this. Whereas an oil spill skimmer, hopefully I'm skimming just oil off the top of a water body. When I'm dealing with trying to recover oil from the bottom, I'm dealing with a much more difficult cut to all of this. So non-floating oil spill response detection and mapping techniques include direct observations. These are divers on the upper left-hand side. Basically, these are divers who are going down, and they will delineate where the oil is by getting into it. ROVs have been deployed with cameras and with sensors. The device on the left is called a V-sor, that is basically sorbents that are dragged across the bottom. And when you pull them up, if they have oil on them, you know there's oil there. So if you GPS that where you dragged it, then you can start developing maps of where the oil is and where it may be going. And then there are breakthroughs that are taking place with sonar devices that by a acoustical principle can delineate what is on the bottom and maybe discriminate oil from water. Now, in terms of containment, I had mentioned that these things are somewhat ad hoc and they're a bit difficult to render quickly for a non-floating oil spill. On the left, those are sorbent pom-poms that are deployed on a fence, and that will be lowered in place near a submerged oil spill in order to capture any oil that is released during a dredging operation. On the right, that is a dredging operation, and that white line in the background, that is actually a boom with a net that extends to the bottom with sorbents deployed on it. The left picture is from a river near Philadelphia, the Delaware River, and on the right, that is in Chicago in the Sanitary and Ship Canal. Now, in 2018, the United States Coast Guard Research and Development Center conducted demos for a deployable boom or barrier that can be positioned on the bottom and will prevent the oil from spreading from where it has deposited on the bottom. So those tests were carried out in 2018, and it is my understanding that the report on them will be available this winter for public review. And this is a picture. I forensically tied this back. This is an incident that occurred probably in the 1980s on the St. Clair River, and they deployed large sandbags to create a deposition area in the river after a heavy oil spill from a dock. Now, in terms of recovery, we have available techniques such as diver-assisted pumping, mechanical dredging, and towable absorbents. While they are used for detection, they're actually recovering oil at the same time. And then waste management, we have on the top, that is roll-off boxes deployed on a barge, and we're putting contaminated spoils into those boxes. Below, from that diver-assisted pumping technique, we are pumping into an oil water storage, separation, filtration, and decanting system. So I'm gonna proceed quickly here because I understand I'm running out of time, and I apologize for that. But this is that operation in Chicago where a submerged oil mass was identified and recovered using a mechanical dredging device. And that is a computer-generated GPS positioning of each cut that is taken by that mechanical dredge, resulting in a picture of what was recovered. And then this case is a case where this is a 3 million gallon oil spill. And it doesn't look like one, does it? And that is because the oil had a specific gravity above 1, and so it immediately sank. So this was a slurry oil in the Gulf of Mexico the barge struck a submerged object after a hurricane, and it resulted in this large spill, and the majority of the oil sank. And so what was selected for that particular recovery was the diver-assisted pumping. So basically, a mechanism was devised where a diver could deploy a nozzle into the submerged oil mass, and a pump would deliver that material topside. And that's the barge that was set up in order to conduct that operation. And this is the diver that was up close and personal with the oil. And this video here, I hope you can see it. This is the top view. This is the diver's view through a video camera, but I want to show you how effective this technique was. That is the slurry oil, and that is the diver's hand, and that is deploying that technique there. And this I would call the perfect example of this technique. This oil separated from the bottom. The sand didn't even come up. It looks like mercury. And so about 200,000 gallons of this spill was recovered in this manner. Now, we are recovering a lot of water in this process as well, but this shows this ability to recover this oil. The depth is about 100 foot of depth. That's a significant depth for a diver to work in. The safety factors are very high. In that regard, my company considered the idea of using a manned submersible device instead of using divers from the safety perspective and from the efficiency perspective. So we developed a concept of using a mini submarine to control that nozzle. We then developed a prototype. We then tested that unit in 2007 in the Rouge River in Detroit. That's the owner of Marine Pollution Control in the front, David Usher, in the submarine to go down and prove the prototype would work. And we were successful in doing that in that particular case. And then we kind of carried that idea forward to a more robust device that included detection techniques and included the recovery device. We developed that prototype further, and then we worked with the the U.S. Coast Guard R&D to take that technology. We brought it to the National Test Facility in Leonardo, New Jersey. This is them loading a test tray with a very 140,000 centistoke oil. And then these trays were lowered to the bottom of the test tank, and our device was used in order to recover that oil. And this video will show that recovery process. So I particularly like the image on the right there. It shows the effectiveness. That is a heated nozzle. That is 140,000 centistoke oil. The depth is not significant, but the idea is that the technique works in order to recover this submerged oil. So let us take a little bit more of a look at that there. You can see the oil mass, while it's very heavy, is moving towards the collection device, and then we will see the nozzle again in a better view there. There we go. So that is that particularly heavy oil at the bottom of a water body being recovered through this methodology, this suction methodology envisioned as being deployed by a 1 or 2 person submarine, commercial grade submarine. So just to finish up, and I'm sorry for running a little bit late, I was asked to kind of look at this topic from the perspective of capability. And being an English major, I started with the definition of capability, and these 2 words struck me very importantly, was first of all ability, which I think we have here, but then there's what really I liked about this definition was potentiality. So how do we build capability? Well, the best opportunity for growth of our skill set here occurs at the interface between the responsible parties. These are the folks that are shipping oil. Companies like mine, which are oil spill recovery organizations, and the regulatory agencies that mandate that all of this takes place. And we do this through drills and exercises, as Steve Keck pointed out to you, area contingency plan meetings and committees, and research and development initiatives. So this is a linear view of what I'm trying to imply capability means to us here. Starts with design and engineering, design systems that can deal with heavy oil, move through proof testing and validation, and then provide training and do drills and exercises to make sure that we're ready to respond, and then we get a response event. But I really don't see this process, being in this business for 28 years, as being a linear process. It's more like this. It's a growth process, so it starts from design and engineering, but it never really ends. And we're always building capability by continuously moving through this cycle. So thank you so much for your time. I hope that this has been valuable to this discussion. And my email is at the bottom, and I welcome anyone to please email me with specific wants or needs. You want this document, you want more explanation of this particular thing. If we have time for the questions now, then I'll do what I can to answer them, but I want to welcome folks to talk to me later on about that as well.
Oh, thank you, Bill. This is Mark again. That was really great and very informative. I think we might have time for maybe one question. And Geneva, do you want to,
Sure thing. I can take it from here.
Okay,
So,
thank you.
hello, everyone. This is Geneva Langland. I'm the communications editor at Michigan Sea Grant in our Ann Arbor office. The question is, what group of oils are mostly moved through the Enbridge Line 5 pipeline right now?
Actually, this is a question that this presentation is not involved in. Those questions should be directed to Enbridge, because I don't know exactly what they are. And my presentation is about heavy oil here. So if you want to email me or contact me, I can direct you to the folks that can specifically address that question.
All right, so it looks like we don't have any other pending questions in the Q&A box. So unless I see something within the next couple of seconds, I think we can call that good on this webinar today. We'd like to thank everybody for joining us. Thank you, Bill, for sharing your work with us. For those of you who might want to revisit this presentation or send it to someone who wasn't able to join it, we will have the video with captions available on the Great Lakes Sea Grant Crude Oil website within a few days. And I'll also send this email out to send the link in an email out to the lists of registrants. So I think with that, if you have any follow-ups, feel free to contact Bill at bhazel@marinepollutioncontrol.com. And we thank you all for your attention this afternoon.